All right. So I'm going to talk about complex numbers uh, in this lecture. So, of course, so far we've dealt with almost all the number system. We've dealt with natural numbers, where we spoke about mathematical induction. Then we did integers. So under integers, we treated many topics, including devices, congruence, modulo, and so on. All those topics come under integers. Um, then we went to talk about rational numbers, where we saw that, of course, rational numbers are types or integers, but now in numerator over denominator, where the denominator cannot be zero. In this lecture, we're going to talk about complex numbers. So complex numbers, you see, if you take the whole number system that we've discussed, we've covered everything. In fact, even in under rational numbers, when we treated irrational numbers, we saw that we take care of numbers. If they're not rational, then they'll be irrational. One particular number that we did not take care of was the square roots of -1, or of negative integers, right? The square root of negative integers. This so far, we have not been able to handle. And so this particular lecture is just to talk about the square roots of negative integers and how they come into play as well. And this brings us to what we call the complex numbers. So a complex number, we define it as if we have x and y, which are real numbers, then if we write a number x plus I of y, we say that it is complex number, and I squared is equal to -1. So this is really, really a critical aspect, that I squared is equal to -1. Of course, in such a case, it means that if you have if you have an x plus iy, if you have an x plus iy, if you have I squared is equal to -1. This is a critical of importance to what a complex number is. Of course, if you have an x plus I of y, then we say that the x is what we call the x here, we call the real part, right? We call the x part the real part. So this part here, we call it the real part. And then y part, we call it the imaginary part. The y part, we call it the imaginary part. So it means that we can say that a number can be full real. If the number is real, then it means the imaginary part is 0. So here, if x is 0, we say that then we have only y of I, and this makes that number a pure imaginary number, right? And then, of course, if y is 0, then we also have a pure real number. So we have a real number, and that is fine. So example, if you take 3 plus 4i, we say that 3 is the real part, and then the imaginary part is 4, right? So that's a good example. Uh, next, the question we need to ask ourselves is, can we add these numbers? Can we subtract them? Can we multiply them? Can we divide them? So this is what we try to now solve. So we say that if you have two complex numbers, x1 plus y1 of I, right? If you have two complex numbers, x1 plus iy1, and then you have another one, x2 plus iy2, then you can add them, right? If you add them, then basically you add the real parts and then you add the imaginary parts. You can subtract them as well. So in this case, you see we have x1 plus y1 of I minus x2 plus y2 of I. If we do that subtraction, we take the real parts, right? So here's x1 minus x2, and then we take the imaginary part. So the imaginary part in this case, we have y1 of I, and then minus y2 of I. Also, so in a similar manner, if we take an example where x1 is 3 plus I, and z2 is I1 minus 2I, then we can find, for instance, we can find 1, right? You can find 1, z1 plus z2, 2 z1 minus z2. So if we take z1 plus z2, then it is 3I plus I minus 2I. And so you take the real parts, right? You take the real part, and then the sign here. And so you write 3 plus 1. And then you take the imaginary part. So the imaginary part in this case, we have the sign here, and then you take this as well. So you have I plus minus 2I. And then you put them together, you have 4 minus I. And we can do the same thing if you want to subtract. So if you have Z1, you take Z2, then you just write 3 plus I, and then you say 1 minus 2I. And so here you take the sign here is critical, right? And then 1, and then you also have plus, you have your I, and then you have the sign here also, but this is minus, and then this is minus 2I. And so in the end, you have 2 plus 3I. So this is how you do addition. You add the, the similar parts. You add the imaginary parts, you add the real parts separately. And this will give you another complex number. If you want to multiply again, so if you want to multiply, then you can see you can just multiply. If you do a multiplication, you multiply x1 plus y1i, x2 plus y2i. If you multiply them, then you get x1, right? x1 times what is in this bracket plus I1i times what is in that bracket. Again, you can expand x1, x2 plus x1, y2 of I. Then here you have y1i times x2. And then here you have y1i, y2i squared, right? And then you know that if we have I squared, then I squared is nothing but minus 1. So this part here, which is I squared, will then become minus 1, which will change the sign into minus. And so in the end, you only have an I here. You only have an I here, and then an I here. You factorize the I out, then you take the real parts out as well. Then, of course, what about division? To divide, for complex numbers, to divide, you need what you call the complex conjugate, right? The complex conjugate of the denominator. So you take, if you have complex numbers dividing each other, then you take, or if the denominator is a complex number, you take the complex conjugate of the denominator, and then you multiply both the numerator and the denominator by the complex conjugate. So for instance, if we take this here, which is x1 plus y1i over x2 plus y2i, and we want to find, we want to solve this. We take the complex conjugate, right? The complex conjugate of, so if we have z is x2 plus y2i, then its complex conjugate is x2 minus y2i. And we take this complex conjugate and we multiply both the numerator and the denominator by this complex conjugate to give us now this form. Then we should not forget the remark is that if you take a complex number z and you multiply it by its complex conjugate, then what you get is the sum of squares of the individual parts, which is the real part x and then the imaginary part y. So let's consider an example for an example. Let's consider an example of solving um, complex numbers in this sense, right? So here, what we are going to do is that we'll take the first one. Okay. So if we take the first one, so we have 2 plus 3i, then minus 1 plus 2i. So what we do, we take 2, take minus 1 plus 2i, plus 3i into brackets, minus 1 plus 2i. We have minus 2 plus 4i plus, oh, we say minus 3i plus 6i squared. And then again, we should not forget that we said I squared is equal to minus 1, right? So when we do that, then we have minus 2, right? We have minus 2 plus, so here we have 4i minus 3i, we'll have I, and then here we have minus 6 because I squared is minus 1, and this will give us minus 2 minus 6 plus I, which is minus 8 plus I. Now the next one is if we have 1 over 2 plus 5i. Again, I said the first thing you do, the first thing you do is find, right? You find complex conjugates. You find complex conjugates of denominator, right? Of the denominator. So here we have, if z is equal to 2 plus 5i, then its complex conjugate is 2 minus 5i. Okay, and then now you multiply the numerator and the denominator by this complex conjugate. So you have now 1 over 2 plus 5i, and then you have 2 minus 5i over 2 minus 5i, which will be 2 minus 5i over, and now you have squares, sum of squares, so you have 2 squared plus 5 squared, and this will be 1 over 29, 2 minus 5i. And this will be how you solve it by division. Of course, another important aspect of complex numbers is we can write complex numbers in terms of in a trigonometric form, right? But to do that, we need to go through certain basic steps, right? So first, the if you have a complex number z, which is equal to x plus y of I, it can be represented in a complex plane as the point x and y. Of course, we'll come to that. If we are in the complex plane, then the horizontal axis, we call it the real axis, and the vertical axis, we call it the imaginary axis. So it is like you draw here where this is a real axis, right? And then your y-axis, you call it an imaginary axis. Yes, come. Okay. Something works.
Math result to you. The first that I came here said that we should add our details on the time seven.
Okay, that's fine. All right. So you have a real axis and then an imaginary axis. All right. So to derive the trigonometric form, first you need the modulus or the absolute value of complex numbers. If we have a complex number z, which is x plus I of y, then the modulus is the square root of the sum of squares of x and y. So if you have z is x plus iy, then the absolute value or the modulus is square root x squared plus y squared. And we can now go on to the next step to deriving the polar coordinates of the complex form. Right? So for the polar coordinates of the complex form, because we are in a complex plane, as I showed earlier, we can write an angle, we can derive an angle theta such that it's an angle, the line, this line Z makes, right, from the origin. If we do that, then this theta, together with y and x, we can write sine theta as y over the modulus. Here, let's call the modulus r. Right? And then cos theta is x over r. Of course, if we write sine theta is equal to y over r, then we can write r in terms of the modulus and then the angle, which is r sine theta. And of course, x in that sense will also become r cos theta. And then finally, we can write tan theta as y over x. So we can write tan theta as y over x. And then this means the angle theta here is nothing but the tan inverse of y over x. So if we have a complex number z, which is x plus I of y, and we know y is r sine theta and x is r cos theta, we can substitute this into the complex number x plus iy. If we do that substitution, then we have r cos theta plus I sine theta, which is r cos into bracket cos theta plus I sine theta. And we know that cos theta plus I sine theta is nothing but the exponential I of theta, and then with the r. So this is a polar form. And now, as against writing z in terms of x and y, as we did here, right now, we can write Z in terms of the modulus, and then the angle is subtends in the complex plane, right? So let's take one or two examples and see how we can find the polar form of some complex numbers as well. So example, if you have here, so here we have 2 plus 2i, and we want to find the, the polar form of 2 plus 2i. Right? So one, we said if you need to find a polar form, then the two things you need, one, so for if z is equal to 2 plus 2i, then you need to compute the modulus r, and the modulus is 2 squared plus 2 squared, which is square root of 8. And the angle it makes, we said, is tan inverse of y over x. And this is tan inverse of 1, which is pi over 4. Pi over 4. And this gives us our new z to be square root of 8. And then we have cos pi over 4 plus I sine pi over 4. Of course, as I said, we can write this as in an exponential form. This will be square root of 8 e I pi over 8. I will say this is the exponential form of the trigonometric function. And the second one, example 2, if you have z is equal to -1 minus square root of 3 of I, then r is nothing but the square root of -1 squared plus the square root of -3 squared. And this will be equal to 1 plus 3, which will be square root of 4, which is 2. Which is 2. And then the angle will be nothing but the tan inverse of minus square root of 3 over -1, which will be the tan inverse of the square root of 3. And this will give us pi over 3. But we'll realize that so if you take z to be -1 -3, this will be here. Right? This will be in this fourth quadrant. Right, so let's call this quadrants 1, quadrant 2, quadrant 3, right? quadrants 3, and then this is quadrants 4. So minus 1 minus, so this z here, right, is the same as saying minus 1 minus square root of 3, which is here. So to find the angle, so what the angle we have found here, which is y, right, over x, is actually this angle here. So to find an angle, from here to here, right, we'll have to consider now, we'll have to consider now we'll have to consider now the fact that we have 2 pi minus this, let's call this theta 1, right? So theta will now be 360 minus that part. And this will be 2 pi minus pi over 3, right? So 2 pi minus pi over 3 will then become 5 over 3 pi. So we have found our z, which is equal to 2, and then we have cos 5 over 3 pi plus I sine 5 over 3 pi. And we can also write in the exponential form 2 exponent I 5 over 3 pi. As I said, this is the exponential form. Okay. Then next is that we can multiply trigonometric functions, trigonometric forms of the complex number, as well as we can divide them, right? So if we have two trigonometric forms, which is z1 is equal to r1 cos theta 1 plus I sine theta 1, and z2, we can multiply them. Their product, z1, z2, is nothing but the product of the modulus of the moduli and cos the sum of the angles plus sine the sum of the angles. If you divide them, z1 over z2, then we have the division of their moduli r1 over r2, and then we have cos the difference in the angles theta 1 minus theta 2 plus I sine the difference in the angles. So for instance, for example, if we take this example here, right? If we take this example here, and then we want to solve, then we say that if we have, so solution, let's take the first one. If you have Z1, Z2, and you want to find the products, then basically Z1, Z2 is nothing but R1, R2, right? So R1 from that, the first one is the square root of 8, and R2 is 4, right? Then we have cos, right? We have cos, then the difference in the angles. So we have pi over 4 minus 4 pi over 3 plus I sine pi over 4 minus 4 pi over 3 as well. And this is nothing but, so right, so this is nothing else. This is going to be nothing else but we'll write here now 8 square root of 8 square root of 2, right? 8 square root of 2. And then now we have cos, right? Sorry, this is the product, so we are adding. So cos, now we have 19 over 12, right? Over 12 pi plus I sine 19 over 12 pi, right? And then of course, we can write it in exponential form as well. So in an exponential form, this will become 8. So Z1, Z2 will be 8 square root of 2 E 19 over 12 pi I, right? Pi I. Okay. Of course, this really means R1 times R2. If you want to write in exponential form, E theta 1 plus theta 2 of I, right? In an exponential form. And then here we have R1 over R2, then E theta 1 minus theta 2 of I. But this is the exponential form as well that you can write it in. And now let's do the difference. So this is the second question. This is question 2. So the question 2 now deals with the difference. Right, it deals with the difference. So we said the difference is you define, so if you have Z1 over Z2, then we said you have square root of 8 over 4, and then now you have cos, you have 4 over pi over 4 minus 4 pi over 3 plus I sine pi over 4 minus 4 pi over 3. So here you have square root of 2 over 2, and then now you have cos minus 13 pi over 12 plus I sine minus 13 pi over 12. And then we have square root of 2 over 2. We have cos 13 over 12 pi plus I sine so this is minus sine 13 over 12 pi. Okay. All right, so here as well, now what we can do is that we want to now talk about the powers of the complex numbers. So if you have a complex number Z, right? If you have a complex number Z, which is R cos theta, R into bracket cos theta plus I sine theta, right? And then you take an N, which is a positive integer, then you can actually find the power, the Z to the power N of the complex number, right? Of that complex number. So in fact, you do not even need this necessarily. There's the same. You can have Z is equal to X plus IY. You can find the powers. They're a bit complicated, but you can still find it. But the Moivre gave us a nice rule for finding higher order terms of complex numbers. That means that you can convert your complex number into the polar form, right? Into the polar form, and then now find the higher order of it. And it just says that if you want to find it, then if you have it in the polar form, then Zn is nothing but R to the power n cos n theta plus I sine n theta. So example, if you have z is equal to 2 plus 2i, and you want to find z4, first you convert, so first convert this, right, this now here into a polar form, right? Convert it into a polar form. Convert into a polar form. And to convert into a polar form, you need modulus, right? So you need the modulus. The modulus is nothing, right? You can see the modulus here. You need to first the modulus, which is 2 squared plus 2 squared square roots, which is square root of 8, which is 2 square root of 2. And then you need the angle, which is tan inverse of 1, which is pi over 4. And with that, it means that we can write our z as the modulus, which is square root of 8, and then the angle pi over 4. Of course, in exponential form, we can write it as square root of 8 e pi over 4 of I. But in the trig form, we write square root of 8 cos pi over 4 plus I sine pi over 4. Now, to write it to the right, to the power 4, now we just apply the Moivre's rule theorem, which says that write your z to the power 4 as modulus to the power 4 cos 4, which is the n, right? The n, and then the angle pi over 4 plus I sine the n and the angle pi over 4. So square root of 8 to the power 4 is 64. Now we have cos pi plus I sine pi. Cos pi is -1, sine pi is 0. So you expand, you get minus 64. Right? And if you use the exponential form, then basically you have z to the power 4, which is equal to square root of 8 to the power 4 exponent 4 times pi over 4i, right? And this will give you nothing but 64 to the power pi of I. And this here is -1, right? So sometimes it's easier in that sense. Then we talk about the nth root of the complex numbers. So we know now how to find the powers of complex numbers, how to multiply, how to divide them. What about how to find the roots, right? The roots of complex numbers. And now Moivre gives us another good idea of how to find the roots. If you have a complex number in a trig form or in a polar form, then the root is nothing but you write the kth roots as wk r to the power 1 over n cos theta plus 2k pi over n plus I sine theta plus 2k pi over n, where k goes from 0, 1, up to n minus 1, right? So let's take an example, and then we will end the lectures on complex numbers. So to do this example, what we have discussed so far is you need certain ingredients, right? So you know your R is equal to 4. You know your angle theta, right? Theta is 60 degrees. Okay, of course, 60 degrees, you can also write it in terms of pi, right? So it's pi over 3, right? It's pi over 3. So you have to be careful with the formula because we wrote it in pi, but you can write it in degrees as well, radians or degrees. So here, then we have k. K we said goes, so we have n in the question says square root, so it's n is 2. So k, we said k goes to 0 to n minus 1, n is 2, so k is k0 and 1, right? So we will start with K0. So K0, we take W0, and W0 will have R, right? We have 4 to the power 1 over 2. And then now we have cos into brackets theta. Okay, so this theta, let's say we use the 60 degrees. So we say it's 60 degrees, but then it means the 2 pi, we'll have to write it as 360, right? And then the k here is 0 over our n, which is 2, plus I, and then a sign, and the same thing again. This is degrees, this is degrees. So 60 degrees, 360 degrees, 0 over 2. If we do that, then we have 2 into brackets cos. So this will be cos 30 degrees, right? Plus I sine of cos 30 degrees again, and cos 30 degrees is square root of 3 over 2, and then sine 30 degrees is half. So if we do that and we multiply through, then we have square root of 3 plus I. And next, we take k to be equal to 1, right? K to be equal to 1. So if k is equal to 1, we have W1, which is equal to 4 to the power half. And then here we have cos 60 degrees plus 360 degrees times 1 all over 2 plus I sine 60 degrees, 360 degrees times 1 all over 2. And here you have 2. Two into brackets, cos, so this is 420, so you have 210 degrees plus I sine 210 degrees. This is 2 cos 210 degrees, cos 210 degrees is nothing but minus square root of 3 over 2 sine 210 degrees. It's also nothing but it's also nothing but I minus half. And this will give us minus 3 minus I. So the two roots, right? The two roots are 1 square root of 3 plus I minus square root of 3 minus I. That will be the two roots that we need. But let me go over again one of the questions, especially in the quadrants, right? One of the questions in the quadrants. So if we want to find, right, if we want to find polar form of the complex number minus I minus 1 minus square root of 3I. And 1, if we have z, so if you have z, it's equal to minus 1 minus square root of 3 of I. Then our R is nothing but minus 1 squared minus square root of 3 squared. And this will be square root of 4, which is 2. And then our theta is tan inverse of minus 3 over minus 1, which is tan inverse of square root of 3, which is nothing but pi over 3. Of course, if we consider the quadrants, right, then this is really in the third quadrant, right here. So now if we go from here to here, it means what we have calculated as theta, right? This, let's call this theta 1. And then now we know that from here to here is pi. So we can add it. So eventually our theta will be pi plus theta 1. And this is theta plus pi over 3 is 4 pi over 3. So our new z is r. Our r is 2, and then our angle is 4 over 3 pi. Right, and this will give us the complex, the polar form of that, which we can write as 2 cos 4 over 3 pi sine 4 over 3 pi.